stuff. We'll find out. So what do we got here? We got z minus z naught equals a, but what do we know a is? Fx at the point x naught, y naught, right? Plus b, but what do we know b is? Fy at the point x naught, y naught. Now real quick, compare this to y minus y naught equals m times x minus x naught, right? And what's m? dy dx, right? So this is extended now, and actually you can just keep extending this however many dimensions you have.
Tangent cube.
Dude, exactly. It's already hard enough to imagine 4 dimensions, but then you have to imagine your tangents are in 3 dimensions. It's like a tangent cube. Oh shit. 2 dimensions get a line, 3 dimensions you get a plane, 4 dimensions you're going to get a tangent. Space actually is going to be crazy.
Is that a U or a Y?
Where are we at?
Here? No, down, blue. There.
Oh, here. Yeah, it's a Y. Thank you. All right. So see how it has the exact same form, does it not? Does it not? Say it does. Okay. All right. All right. That's enough of that old stuff. Now, real quick, while this is here, actually, let me see what I'm going to do. Let's do a concrete example very quickly. Let's say one right out of the homework. You know, near the homework. Yeah, let's do number 3. Number 3 says this: find the equation of the tangent plane to this surface at the point 221. Real quick, double check the book, make sure they got it right. Does that surface go through that point? That's what they're claiming. Those people, you never know. Who wrote that book? I don't know this person. I thought Jimmy Stewart died. Different Jimmy Stewart. Yes, it does. 2 minus 2 is 0. You did the 0 is 1. Sweet. I like it. Cool. So there is a point that is on this surface. I'm going to find the equation of the tangent plane to this surface. So what do I have to figure out? I know the point, so I know x naught, y naught, z naught. I just have to figure out fx. And what is fx really related to the letters that are given to me in the surface? What's another way to write fx? Partial d?
Oh, partial d x d. Partial
Z.
z x.
Partial x. Is that cool? Let me stop there for a second. F replaces z, just like F replaced y a million years ago for us, right? Roughly a million. So fx is the partial of, I could also call it partial of f with respect to x and partial of z with respect to x, but I'm going to call it partial z because that's what they gave me was a z. Makes sense. If you don't use that same, who gives a crap as long as you do it correctly. Yes?
Should use d. It would be much easier. Easy dx.
To do what? Oh, usually go p instead of a d?
Yeah.
Oh, I got you. Too bad. You weren't around. So what is dz dx? Again, just to make sure everybody's with me, what does that mean? I'm holding what constant? Y is now a constant. This is like e to the x minus 1 or something. So how do you take that derivative? It's just going to be... That's crazy. And the only difference with fy, partial z with respect to y, is if y is the variable, it's negative. So when you take its derivative, negative e to the x minus 1. I like it. So now to finish filling this in, I got x naught, y naught, z naught. I need f of x evaluated at the point in the domain, and fy evaluated at the point in the domain. So what's fx evaluated at 2, 2? 1. And what's fy evaluated at 2, 2? Negative 1. So go ahead and just take a minute and write down the equation of the tangent plane. You're done, basically. You just got to collect it all together. Alright, I'll catch up to you guys. So it'll be z minus 1 equals, yeah, so that'll be 1 times x minus 2. I'll just do that just because. Plus, yeah, so plus fy, and fy is negative 1, so minus y minus 2. So z equals, yeah, x minus y plus 1, because the negative 2 plus 2 goes away. Alright, now, let me stop there for a second. So I don't know if you remember, and I'm not sure if you didn't have me for Calc 1, I'm not sure how your Calc teacher taught you this, but linear approximations being a separate section is hilarious. That's why I like the way they did this. Linear approximations are tangent lines in Calc 1. Linear approximations are tangent planes in Calc 2. There's no separate process for it. So what does that mean? What the hell did linear approximation mean? What's it useful for? What's the relationship between what we just found and the original surface?
Go a little bit, you're going to be within this much of this.
Exactly. So it gets a little bit harder. I don't know if you guys remember, and again, it all depends on who you had as a teacher. But there was you had a curve, and then you had an approximation to that curve, right? So let's say right here. And then you had to figure out, well, how far can you go out so that it's within so much? So you have the error tolerance part of this. So that sounds familiar to some of you, and to some others it might not sound at all familiar because you had evil teachers that weren't thinking ahead for you. Yes?
So this was finding point where...
Which part are we talking about? This? This is the equation of a plane. I like it. And they have to give us the point that they want me to find it at. So they have to give me a point to find a tangent line. Same thing with the tangent plane. I like it. I don't know if you guys realize how we sort of circumvented directly doing a cross product of these vectors that we'd actually have to find in the first place. Right? Thank God we circumvented that by just looking at the coefficients in a different way. But you could do it that other way if you really wanted to. It'd still have to work. Alright, where was I? Oh, okay. So, close to this point. Close. And we should all hopefully understand that that word is remarkably ambiguous. It depends on how tolerant of error you are. So if we're not sure about anything, which we aren't, we shouldn't get very far away from that. So if I wanted to know the value, the output for an input of 2.01 and 1.98, Z would be approximately what? I could just use this. Let's check it. Well, first off, the best check is this point has to do what here? This point has to be perfect, because that's where the damn thing touches, right? That's where my tangent plane touches. It should be perfect there. So as a real quick check, that point better work in your tangent plane equation, or else you did something wrong. Does that make sense? So 2 minus 2 is 0, plus 1 is 1. Thank God 2, 2, 1 works. Yay. Okay, good. That's a quick check. You should do it. So now let's do this. What do you get when you plug in 2.01 and 1.98 here? What's 2.01 minus 1.98? 0.03 plus 1? 1.03. Crazy. Now somebody help me out. In your calculator, do e to the 2.01 minus 1.98.
1.0305.
Yeah, we got pretty close. So this said at the point 2.01, 1.98, it gave me an approximate z of 1.03. The actual z was about 1.0305, blah, blah, blah. Right? Does this sound familiar? It should feel just like linear approximation stuff. Find a linear approximation for square root of x and then estimate the square root of 4, whatever. All right. So this is obviously an important little equation here. And it's just really going further with the equation I erased, the one that we're used to. The y minus y is really y minus y1 equals m times x minus x1 gone one step further. All right. Enough of that. That shouldn't be too freaky. Now, everybody's got this here, right, that wanted it. Or even if you didn't want it. So everybody got this here? All this stuff here? Because I want to build off of this guy now. Some more stuff, believe it or not. We're going to do one of your favorite differentiation rules. The chain rule. Yeah, I was being sarcastic, sorry. What's that, chain rule?
Yeah, compared to...
I totally love chain rule, but it's evil because people forget it. Quotient rule sucks so much. But I never did quotient rule when I was a student. I kind of warmed up when I became a teacher because some functions are a little bit easier to do, but I just always did product rule. You just always take the bottom, make it to a -1 power, and attack it with chain and product rule, right? But then you got to find an LCD maybe, which is always easy to be honest, but oh well. Anyway, if you like your quotient, if you even know a little song about it, my song was top first. That's it. That's all the song you need. Not this high below crap, whatever. Now watch. Let me write this. Let me allow this distance to get really small, stupid small, infinitesimally small.
What's the symbol for an infinitesimal? It exists now. I forget what it was.
Do it again.
What's the symbol for an infinitesimal?
Well, this is the representation of an infinitesimal change in the z direction.
No, there's this actual thing. It's like 1 over infinity is equal to...
Iota. Yeah, look it up. I forget the symbol, to be honest, which I hate because I love the idea of iota. It explains why the probability of a single thing is 0, but the probability of the sum of things is not 0. Because it's not really 0, it's actually sort of the inverse of infinity. Iota. Alright, enough of that. You can Google that later. So dz, let me just write this as fx, so I don't have to write all crap. This I'm going to replace, of course, with, what do you think? Dx. I'm going to let all these distances get really tiny. dy. Alright, is that cool? Now, if I had, if I want to write something kind of silly, if I had this, let me see if you guys are cool with this idea. You see how in 2D, this is silly, but it still has meaning. It still is the derivative of the function with respect to x. But in here, it wouldn't be a partial because it's not partial because there's only one independent variable in the first place. So see, if I do this, and then divide by dx, I get dy dx equals the derivative of the function with respect to x. That's amazing. That's amazing. Let me stop there for a second. Are you guys semi-cool with that? I wanted to do that because that's old shit. That's Calc 1 stuff. I'm writing fx, but we should understand that actually means the total derivative, not the partial, because there's only one variable. So here, can I do the same thing? Can I divide by something, a single thing, and have it work the same way? No. Shit. So this is the total differential, but it's kind of built of these differentials. You can't write a single statement. But I can build off of this. Yes? You okay?
Never mind.
So if my x is some function of t, and y is some function of t, I can then divide everything by dt and get... And actually, let me write this better. What is fx? Write it full out. What's it look like, fx? The partial of z with respect to x. And this will be dx dt plus partial of z with respect to y, dy dt. So this isn't strictly allowed, even though we play around with these things all the time the same way, because this truly is in some sense a ratio. So it's okay to do what we just did. What I'm about to say is completely not okay, but it's kind of nifty. These sort of cancel in a way, not really, because that's not really the same d as that is. But do you see how that's looking at dz dt and that's looking at dz dt? So when you combine those efforts, you're going to get the whole dz dt. So how quickly is something moving? It's going to be composed of how quickly is it moving in the x kind of direction, how quickly is it moving in the y direction, which is what this says directly. But this is how I build it in if it's all parametric. If it's all based off of this t. So let's do so here's a point equation. This is actually the chain rule. Yes, sir? No, yeah. In section 13.4 is a very specific application of 13.3. But in general, the parameter can be whatever. It doesn't have to be time. It's very often time, right? Because we just use it in the real world, and that's sort of the behind-the-scenes variable, time, that's letting things change. I like it. Doesn't even have to be something that starts with the letter T. All right. So let me see. Let me pull another problem out of the homework section. Yeah, we could do that. So let me make sure you understand. This is what's called the differential. I call it the total derivative. I think they reference it like that also, but maybe not. Total differential. All right, sure. Let's see what else they call. Nope. Okay. Too bad for us. Oh, I'm getting. Oh, that's right. It's over here. Here we go. So let's do this. Here we go. Number 1 in the book. Believe it or not, we're in the chain rule now. So what I want to find is dz dt. So let's see what you guys think. Yes?
Do you need to have these parametric equations here to do the chain rule?
I couldn't calculate this without them, right?
So why does it have to be that way though?
You have to have some understanding of the dependence on t, or else there's no way to calculate how z changes with respect to t. You see what I mean? If your question is, are there other ways to do this where you can bring that information in later? Yes.
Okay.
I think that might be your question.
Chain rule?
This is the chain rule, because I want you to remember, what does the chain rule say? In fact, the very first part of this is related to the chain rule. So I don't know if you guys remember df of g with respect to x, right, was df with respect to x, well, with respect to g, times dg with respect to x. So this is like that chain piece. This is the derivative of the inside function. That is the chain rule. So see how it's the same idea here, except now I've got two pieces to it. Yes?
So, what we're doing here, are we going to take the partial of z with respect to x and then multiply it by the derivative of those parametric?
Yeah, so what do you need to figure out? This you can look at this as a building, a construction kind of problem. I need to know what the partial of z with respect to x is. All right, so what's that going to be? What's the partial of z with respect to x? Okay, so we get a good beginning. Y cubed. All right, let me stop there. Please, dear God. Do you guys understand that? Partial derivatives are going to rule our life for a little while. Therefore, you must understand them. Y is a constant when I do this. So it's just like 5. If I had 5x squared, its derivative would be 2 times 5 times x, 2 times y times x. Yes?
What can change this from a function with 2 variables to a function with 3 variables?
Well, let's keep going. You ready? So what's the partial of z with respect to y?
3xy squared.
All right, good. So 3xy squared minus x squared. Beautiful, because x squared is like a coefficient of y now. I like it. So we got this piece and this piece. Now I need this piece and this piece. Keep going. Got you started. Keep going.
You can take the derivative of dx dt, which is 2t.
Yeah, that's all you need here.
Oh, that was the plug in the
x. Yeah, that's
This is 14. Jeff, it's 14.
No, this is 14.5. Yeah, snuck into 14.5.
This part right here.
Because they bleed over to each other anyway, yeah.
So then when you're plugging it into like the GBT formula, you've got like 2 squared plus 1 in every x.
You could. You
Is
could.
that how you like, or do you like how would you want us? Well, how
All right,
would
let's
you
put it
work
together. You ready? Let's put it together. So what do you get for dx dt? 2t, and dy dt. That's crazy. So then you get for dz dt, you get y cubed minus 2xy times 2d plus 3xy squared minus x squared 2t. So you can like factor 2t out. You could replace x and y with their t definitions, right? You totally could, but normally you don't. If I said evaluate this, let me see how they're going to ask you here. Do they ask you? They should. They should. No, they don't. Oh well. Oh yeah. Okay. So if I said find dz dt when t is 1,
Oh, we'll have like.
then I would rather leave it like that. Because now, if t is 1, what's x would be 2 and y would be 0. Right? If t is 1. Is that cool? So in that respect, if they say find dz dt at a specific value of t, then I'd rather just leave it like this. Does that make sense? Now, if you want to write it, if they don't say that, you have the option to write this. You can plug into y what it is, but you can see how that gets really quite disgusting, right? There's really no purpose, because normally the next thing you're going to want to do is for a specific parameter value. So you'd rather work with it like this.
will they give you like a parameter value that has to do with X and Y? Instead of like T equals a certain number?
We've seen that kind of before, but they won't really do that here. When they do that, they have to be very careful to give you something. Like there was a bunch of cosines and sines. So they would say at the point 0, 0, so you know that sine is 0 at pi or 0, so you know that that's got to be what t is.
Right.
Does that make sense? So it's got to be something really obvious, but they're not going to do that to you here.
This is y cubed minus 2x, right?
Yeah, just this here.
Okay.
I like it. Just plug all the stuff back in, yeah.
So this isn't, I mean, it's not that it's not new, but it's just a new way of doing it. We could still do this if we just plug the t's in.
Totally.
Wait.
But what the chain rule does for you is it makes things quicker. For example, just to remind you guys.
For weird pyramid.
Yeah, not even weird. This isn't very weird. So you could multiply this out and not do the chain rule. How many want to do that? Oh, good. Get started. I want you up here on the board. If you need more board space, you can use the next room. Continued on next board in the next room. Okay. No, you don't. You're not serious. All right. So chain rule saves me from having to evaluate the function fully. Does that make sense? So I didn't have to plug these in and then cube them and so forth. Now you could plug them in. All right, let's try this. Let me see, where am I? Yeah, let's take all this. Now watch this. If you plug them in, do I really want to do all? I don't really want to. If you plug this in, don't even multiply them out. Do the chain rule like we're used to. It would be the same thing you would get if you actually plugged them in now. But the usefulness of this is so often you don't need that other form. You don't need something specifically only in terms of t. So why go through that trouble? So the chain rule is sort of a shortcut. Like it was before. I didn't have to do the 40th power, thank God. We have the chain rule. Same idea here. I don't actually have to plug them in and do anything with them. I've got this chain rule. Yes?
But this is kind of stepping away from our surfaces now. That's still a 1D thing.
Yeah. Since these are dependent on a single other parameter. So we're about to go, what if they're dependent on...
Our partials now.
So what if they're dependent on two parameters? So let's go there.
They aren't.
They will be. All right. Oh, I do want to do that, but let me do this first. So you might be able to imagine. All right. Let me give you what the problem looks like, and then we'll talk about how to do the problem. Yes.
The 2 and 0 on the x of the x equal and y equal. Where'd you get this?
Oh, sorry. That was if t was 1. Then I can plug a 1 in for t, and I can plug a 2 and 0 in for x and y. See, so it's quicker to do this than it would be to plug that stuff in and then go through that. Because I can quickly evaluate it for some given value of t. I don't need dz dt in terms of t alone. I don't need it. If you did need it, you could do it. But we normally don't need to go to there. Okay. Coming back to this. So this was earlier, right before I divided by dt. So amazingly enough, if I divide by some other parameter, I get the same idea. It's amazing. Bless you. So a problem could look like this. I just did the opposite of what I said it would do, but we'll be all right. Oh, here we go. So I could have a problem that looks like this. Oh yeah, that was good. Yummy. Now, this is sort of bringing in something that was brought up earlier. This would be, what would this look like three-dimensionally?
Let's see what that.
I like it. So it would look like just a space curve. It's not going to be a surface, right? This, though, now how many variables define this thing? 2. There's two hidden axes. I normally have the t-axis hidden from sight, but now I have the s and the t-axis hidden from sight. So I don't think they, I wish they would have, I don't think they did. I'll see if I can't get some image to show you what this would look like. There are some out there, but they don't give us any general, shoot. Too bad for us. But the question is going to ask, find dz ds and dz dt. So now I've got this in addition to the earlier one. They're both the same damn thing. You just have to find them one at a time, yes?
Would this not be partials?
Oh yes. How did I write them? Because now I'm taking with respect to s and with respect to t. Did I write that the same way? Cool, I like it. So anytime you have